Good morning, everyone, and welcome to the 5th episode in the Plastics Refocus virtual webinar series. My name is Ashley Hood-Morley, and I am going to be hosting your session today. Just a few housekeeping items before we get started, and we're going to dive into some really good content that we have today for you all. So first of all, I want to thank our sponsors, as always, Midland Compounding and Consulting, Plastics Machinery Magazine, Plastics Recycling Magazine, and Star Plastics. As I've said from the beginning, we can't thank these sponsors enough for their contributions this year and allowing us to take this crazy year and a great in-person meeting that we have planned for you guys and turn it into some really excellent virtual content. So thanks again to our sponsors. Thanks also to our media partners who help us get the information out about these great webinars every month. So we've got Mold Making Technology, Plastics Machinery Magazine, Plastics News, Plastics Technology, and Recycling Today. Next year, we hope for a lot of great things to happen that we didn't get to do this year. We look forward to seeing all of you at MPE 2021, as well as don't forget to save the date for 2022 when we have the whole program that we have planned for you guys this year in Cincinnati. So save those dates. And then lastly, just a few housekeeping items before we jump right in. So all attendees are currently muted. We will offer a Q&A session after our two speakers give their presentations today. So please keep in mind when you're posing questions that we will still abide by antitrust rules and refrain from answering questions that are related to pricing, production, marketing strategies, anything that could be construed as market manipulation. So we invite you to send in your questions via the Q&A tab on your screen through the Zoom webinar platform, and just keep in mind what type of questions that we'll address during this session. Finally, I'd like to just notify all attendees this is a public education session where members and non-members of the association as well as press may be present. We will not be conducting any official business of the association today. Please note that this session is being recorded and it will be made available to attendees post-webinar. So you should expect an email from us with just a short few questions that we would love to hear from you on in the form of a short survey, and then you will at the end of that survey be redirected to a recording of this session for you to look back on. So with that, try to keep the housekeeping short and sweet today. We want to dive right into the good content that we have. We're really happy, again, new solutions for untapped feedstocks. We're going to dig into a lot of details on advanced recycling today. So I am going to turn the session over to our moderator, Donna Davis. I just want to give her a quick introduction. I think many of you know Donna. She is a legendary in this plastics industry, but with that, I will say she is the Sustainability and Advocacy Manager for Polyethylene at ExxonMobil in Houston, Texas, for her day job, although she does a lot of excellent volunteer work, such as being active in efforts such as the new and market opportunities for wrap collected film and other plastics recycling committee activities. Donna chairs our events and education subcommittee, which puts on the Refocus conference every year. So a lot of the things that we're bringing to you guys this year, Donna has led the efforts on making these things a reality. Prior to her role in sustainability, she serves as a technology scout for new business development. Donna is a member of the Plastics Hall of Fame and a fellow and distinguished member of the Society of Plastics Engineers. Her industry activities include conference organization, in particular, Refocus 2019, the SPE International Polyolefins Conference, SPE's Antec, and the SPE Flex PackCon. So without further ado, I am going to put you guys in the great hands of Donna. And Donna, I will turn off my video and let you take it away.
Thanks, Ashley. Welcome all. Indeed, when we were planning this year's event, we realized that advanced recycling is one of those hot topics and everybody wants to know more. But we think that a lot of people think advanced recycling is one thing, when in fact it's a whole suite of approaches. So this webinar is intended to introduce you to the various approaches to advanced recycling. And that's going to happen with Charlie Willard. Charles is a senior research associate at Lux Research in Boston. He's a member of the Accelerating Materials Innovation team, and he conducts research and market analysis for clients interested in plastics recycling, power to chemicals, and lignocellulosic materials. Prior to joining Lux, Charles received his BS in chemical engineering from Rensselaer, where he conducted laboratory research in electrospinning, cellulosic fibers, and tissue culture of human bone marrow stromal cells. Prior to Lux, he also worked with Arcadis US and multiple academic collaborations in environmental consulting. He's going to give us an overview of the various approaches to advanced recycling. And then I think he'll probably say in the end, no matter what approach you take, you have to feed it something. And so Joe Vaillancourt is going to talk about that. Joe's the president of Cyclyx International. He brings more than 25 years of operational, financial, and strategic experience in industrial, environmental, and energy innovation and infrastructure development. Throughout his career, he's led in excess of $2 billion of debt and equity financings, as well as merger and activities. He has helped commercialize 15 environmental technologies, working closely with large strategic companies and private equity firms in the energy and industrial sectors. Prior to Agilex and Cyclyx, Joe spent 15 years at Waste Management, where he was one of the founding members of the corporate venturing group responsible for developing new and innovative growth platforms in the environmental, sustainability, solid waste, recycling, energy, and clean tech sectors. He's also had various roles in founding more than 10 companies in a diverse set of industries. He has a BS in finance and an MBA from the University of Massachusetts at Lowell, where he also is an advisory board member for their Manning School of Business. Welcome, Charles and Joe.
Wonderful. And so, Charles, I am turning the slides over to you. So you should be able to control the screen momentarily. Excellent. So it looks like you've got it, Charles. Just don't forget to unmute yourself and you're free to take it away.
Sorry about that, Ashley. Could not find the unmute button. Well, thanks, Donna, for the great introduction. As you mentioned, I work for Lux Research, which is a strategic market intelligence company, which really allows me to have a really unbiased perspective when evaluating the technologies today. And today, I'm going to be doing just that, giving everyone an introduction to what the future recycling systems might look like. We're going to do that by first providing some background into the global events that have been so disruptive to the plastic waste trade over the past several years, introduce several advanced recycling technologies poised to take advantage of recent events and capture substantial market shares, and finally, because we are still in a period, and hopefully it'll become evident, of really fluctuating recycled scrap and plastic prices, introduce what we might think happen as the market begins to equilibrate. So first off, I'm going to start us off by introducing some key reasons why the end-of-life markets have seen so much attention over the past couple of years. And I do apologize if at least this beginning section is a little bit of review for some people on the call, but it's important we're all on the same page before I begin introducing these recycling technologies. So our story really begins in the beginning of 2018 with the Chinese national short and subsequent Southeast Asian plastic waste import bans, which have caused global and especially North American recycling to decline drastically. I don't want to get bogged down in too many details here, but the recycling infrastructure is generally broken down into two key segments. You have your material recovery facilities, or MRFs, which collect, sort, clean, and bale plastic waste for resale, while recyclers, which are a different segment, usually a different stakeholder, will purchase this baled plastic waste, process it, and produce recycled materials. Prior to 2018, when all these plastic waste import bans came into effect, MRFs were present across the country, all widespread across the United States, but many of their buyers, the companies that do the actual buying of this plastic scrap and actually do the recycling, were located overseas. With a substantial portion of this buyer's market essentially disappearing overnight, plastic waste collected by MRFs, generally called plastic scraps, are much less valuable than they were before. And this has had the effect that you might imagine. MRFs across the United States are still collecting the more valuable plastic scraps. Think low plastic numbers like polyethylene terephthalate, high density polyethylene. Those recycling numbers are still fairly high, but recycling rates for higher plastic numbers, think 3 through 7, has fallen drastically. And although I am going to focus mostly on the US here, this is not a United States only problem. Although poor domestic recycling capabilities are causing landfills to fill up with plastic, Europe is turning to more incineration of plastic than ever has before. And regardless of geography, plastic is notably finding its way into the environment more often and more readily than is socially acceptable. And government organizations are certainly not blind. Seeing this developing problem, they have been scrambling to implement policy and put forth programs to better manage their waste and encourage domestic recycling capabilities through policies like recycled content requirements or extended producer responsibility policies. And now these policies are widespread and especially strong in certain geographies such as Europe. And while these extended producer responsibility policies are a little bit more complicated and would take a little bit more time than we have today to explain, it's very easy to see the practical and potential impact of certain recycled content requirements. For example, in 2018, Europe introduced a recycled content requirement requiring all PET beverage bottles placed on the European market after 2025 to contain at least 25% recycled content and 30% after 2030. This policy was subsequently copied in Canada, and actually between the time of making these slides and now have come to California. California specifically requiring 15% recycled content by 2022 and 50% after 2030. So a slightly more aggressive policy. And this policy is an issue for mechanical recycling, the incumbent recycling technology, what you think of when you hear recycling. Mechanical recycling really only separates and physically treats plastic, so certain dyes, polymer additives, and other contaminants are not removed during the process. As a result, most rPET, or recycled PET, cannot be used for these food-grade recycled content mandates. In fact, only about 7% of all mechanically recycled rPET can be used in food-grade applications. So seeing this is a huge market gap and a big opportunity for new recycling technologies that can produce higher grade recycled PET. And one of the main reasons one of the advanced recycling technologies we'll be discussing in a couple of slides has received so much investment and attention from beverage industry giants like Coca-Cola and PepsiCo. Now, not only is there a legislative drive, but waste accumulation has also become a huge issue in consumer packaged goods and other product categories due to customer worries about sustainability. We can clearly see this impact through the Ellen MacArthur Foundation, an organization coordinating an industry-wide response to the waste accumulation crisis. The EMF actually began with just 13 individual commitments to using more sustainable packaging, set up in early 2018, but today is ballooned to over 400 organizations. I should also mention that the Alliance to End Plastic Waste, although it's a little bit more on the material supplier, are generally more of the participants in that industry foundation. That is also a very notable one to track. Now, if we look at these initial 13 pledges alone, just sort of taking a microscope in and looking at the Ellen MacArthur Foundation, these 13 initial pledges represent a significant portion of the overall packaging space, impacting up to 11 million tons of virgin plastic if completed. However, there is nowhere near this much sustainable packaging materials available today to meet that demand. And some of this gap is going to be closed by traditional mechanical recycling expansions. In fact, despite everything that's been going on with COVID, the pandemic, the slowdown in recycling when it was first discovered and spread to the United States, North American recyclers are still reporting record high revenue numbers in 2020, which has led to a significant number of recycling expansions that are now anticipated over the next few years. But when you take a closer look, there's actually a pretty big disconnect in individual recycling categories. For example, Nestle and Mars both need flexible, food-grade recycled packaging to complete their initiatives, but this is extremely difficult to supply through mechanical recycling. So different technologies are needed. Now, before I move on, I do want to throw in a word of caution when showing off these company-initiated pledges. As we all know, sustainability has become an extremely pressing issue in the media and on advertising. So many of the consumer-facing companies now making pledges, part of that 400 organizations in the Ellen MacArthur Foundation, they didn't necessarily have a choice of joining or making these pledges. It was either get on the sustainability bandwagon or get left behind and lose customers. Because of this, and quite frankly, a history of brands overpromising and under-delivering on sustainability promises, my team is really hesitant to assume, for example, this 11 million tons of pledges is going to translate to exactly 11 million tons of sustainable material demand. That's not to say some or even most of these companies are not taking these pledges seriously and are not on track and dedicating substantial resources towards obtaining their goals, but you should at least retain a little bit of skepticism when evaluating these announcements. If one of your customers, for example, if you're a material supplier, one of your customers is making one of these announcements, you should really be, going to that extra level, digging a little bit deeper, looking at their overall, their year-by-year financial results, seeing how much funds are dedicated towards obtaining these goals, and is it realistic? I also want to mention that a little caveat here is that a lot of these pledges are simply saying sustainable material demand. I'll talk about it a little bit later, and we don't necessarily have the scope to go into all the compostable, bio-based, biodegradable options for these sustainable material options. But in general, most of this demand is likely going to be fulfilled through recycled plastics rather than those other bio-based options. So with the background out of the way, we'll be taking a look at these different recycling technologies, namely depolymerization, pyrolysis, and solvent-based recycling, in the next several slides. This section is going to contain several cost models for the individual processes. So before we take a look, I want to quickly explain how they were generated, and especially for those of you who are not familiar with Lux Research or have never worked with a strategic market intelligence company like us. So what we do is we really specialize in analyzing pre-commercial technologies and companies, which has led me into dozens of discussions with many developers of these technologies. There is a quick spattering of technologies on this slide. That's not a full list. But when we evaluate these technologies, and when I was really building up the space, me and my team was building up the space, it quickly became clear that to really analyze their real commercial viability, we would need to build several fairly complex cost models to evaluate their various viabilities in various scenarios. And this was especially important right now and over the last couple of years, because as I mentioned, plastic scrap prices, recycled pellet prices are so out of equilibrium that if you look at, and you'll see in a couple of slides, a couple of these cost models, it can give you somewhat ridiculous results. So you need to be able to have a model that's adjustable for different sort of, if you can equilibrate price, if you can say, okay, where do we expect prices to go inside the next 5 years? We wanted to have a model that would be able to capture all that information. And so to build these cost models, we started out with a really basic model based on papers, IP, really get some of the information like thermodynamics in there. And then the more important part was we checked in with all of our contacts who are themselves building these models for commercial scale operations based on their own data. And really from that, we were able to add the complexity that we needed and make sure that we were on the right track with these cost models. And the last thing before I get into the technology descriptions, I do quickly want to clarify some of the nomenclature surrounding these technologies. The term chemical recycling is thrown around a lot, and honestly just really means any thermochemical process breaking down waste, and can be used to describe depolymerization, pyrolysis, and even gasification. So I'm just going to be sticking to the exact terms depolymerization and pyrolysis during this talk, so we're all on the same page here. And you may have expected to see gasification on this list, but most of these companies do not focus on plastic waste streams within the gasification landscape. In fact, Powerhouse Energy Group is really the only gasification company doing anything with plastic. So to start, we need to establish our baseline technology, mechanical recycling, which has been around for decades and is therefore very optimized, very well known. And although we're seeing a few innovations pop up over the past few years, like automated sorting and new feed systems, we do largely know most things about mechanical recycling. In fact, when we were building the cost model for mechanical recycling, this was the model that we had the most information on. There's a lot of studies out there that talks about the different efficiencies with different types of collection streams and different factors that can go into it. So what mechanical recycling does is it pre-treats plastic scraps with, and this can include a whole host of the processes like what you sink float, sorting, washing, and basically you get everything down into one type of plastic or one type of material, and then you simply melt down that plastic material and re-extrude, recycle your recycled pellets, which can be used for other applications. And earlier, we talked about some of mechanical recycling shortcomings when it comes to removing certain contaminants like organic waste, dyes, plastic additives. But the main thing you need to know here, and the thing that I really want to emphasize, is that mechanical recycling, it is so well known and so low cost that when these type of contaminations don't exist, in other words, you're dealing with an easy to separate, clean feedstock. Think something like beverage bottles, PET beverage bottles. It's going to be the winning technology. It's going to beat out any of these advanced recycling technologies. And this is especially true in the strange economic situation we currently find ourselves in. As I mentioned, scrap prices, the feedstock for mechanical recyclers, is the cheapest it's been inside of years. Their products, the outputs, recycled pellets, are more expensive, selling at higher prices than they have been for years. And these factors combine to give us something like the cost model you see here on the slide for high-density polyethylene, which has a huge profit margin. And now, although this graph might seem a little bit unfeasible right now, let me just mention once again, these are very unusual times. As you'll remember, I mentioned that North American mechanical recyclers are currently seeing record high revenues this year. But as this graph shows, when you plug in pre-China National Sword scrap numbers and recycled plastic prices into our cost model, aka prices from 2017, your profitability goes down considerably. And this is what you're seeing on the slide for polypropylene, high-density polyethylene, polyethylene terephthalate recycling. In each of these sections, the two bars to the left represent production costs and revenue using current prices, while the 2 bars on the right represent what happens if we go towards 2017 prices. Keep in mind too, for these cost models, especially for mechanical recycling, for example, you might see that HDPE, the projected is an unprofitable process. We are basically using a cookie cutter formula for this cost model in particular. If you're able to optimize things like owning your own trucking fleet, for example, that might improve your profitability quite substantially. Still, I don't want to understate that mechanical recycling, especially now, is going to beat out any other recycling technology in easy to handle, clean recycling streams, and is going to continue to be the most common type of recycling for the foreseeable future by volume. Now, unlike mechanical recycling, which really relies on this clean, easy to separate feedstocks, very separate collection, MRFs are going to have a big factor on the overall yield of the processes. Depolymerization, on the other hand, our first advanced recycling technology, is the complete opposite, relying on hard to recycle PET waste streams to avoid competition with these mechanical recyclers. Now, depolymerization is a process which goes in and chemically selectively cleaves PET polymers at certain points of the chain to produce monomers that can be repolymerized into food-grade rPET, equivalent to virgin PET. This is going to depend, the exact process that you use is going to, or the exact reaction that you use, the exact solvolysis reaction that you use, is going to vary what exact products you get. For example, hydrolysis is going to produce terephthalic acid and monoethylene glycol, the common precursors for PET polymerization. But a couple of the other processes, like methanolysis, will produce other types of monomers that aren't as traditionally used for PET production. Now, depolymerization can process almost any feedstock containing PET, although there are some notable inhibitors, and I want you to remember this. One of the biggest notable inhibitor that has really limited expansion to date is nylon, which limits the opportunity in certain key waste streams. And what happens when you include some of these inhibitors is essentially they get broken down alongside PET, and it gives you a mixed product waste stream that can be very hard to separate even by distillation. It's really hard to precipitate a lot of these components. So you end up getting an unusable bucket that's hard to separate at the end if you have some of these contaminants. And I don't want to get into too much of the technical weeds here. We can during the questions if anybody has any, but there is still some potential to improve the process. As I mentioned, there's 3 different buckets that we usually place all the depolymerization players into based on the solvolysis reaction they use: hydrolysis, glycolysis, or methanolysis. But this key thing here and the differentiating factor is actually the reaction accelerant. How fast can you make this process? And accelerants are, they really do range, and this is where a lot of companies differentiate themselves, is they can range from catalysts to enzymes to delivering energy in unique and interesting ways. But the gold standard ultimately is usually less than a 4-hour reaction time. And for those who care, this next cost model is based on a hydrolysis-based process, but in retrospect, this model was built inside of late 2019. In retrospect, I'd probably argue that it currently looks like glycolysis reactions have the most momentum. And looking at this slide, one of the key things that you're going to notice is critically, feedstock cost is inside the revenue column. This is because depolymerization developers target what is typically considered unrecyclable waste feedstocks, which allows them to charge a tipping fee to accept their feedstock. Remember, I said that they can really recycle any PET feedstock, no matter how dirty it is, no matter how many plastic additives there are, as long as it doesn't contain key inhibitors. So, for example, let's say that a carpeting company needs to send its polyester-based carpeting waste to a landfill for, it's going to depend on where you are, but let's just say $150 a ton. A depolymerization player will go in and offer to accept this waste for $50 a ton. This is an obvious win for the carpeting company. You're both saving money, and now you get to talk about how sustainable you're being, have a nice press release. While the depolymerization player, now they have a negative feedstock cost. There's also a ton of synergy, as you can probably imagine, between PET depolymerization technologies and PET resin producers. If, quote unquote, bolted on to resin producing facilities or basically co-located on the same site, both the manufacturing scraps from the resin producing facilities can be fed directly into the depolymerization process for an easy recycling, and the depolymerization products can then be fed directly into resin production. And this is really key for a couple of the technologies. You remember I mentioned hydrolysis produces the traditional feedstocks for PET resin production, but for example, methanolysis produces DMT and MEG, what the feedstocks that were used in a couple of decades ago. They're the most common feedstocks for PET production. So methanolysis players, for example, really need to partner with a company that knows how to utilize their products, these little bit weird feedstocks for PET production. And so this bolt-on strategy is generally what we see the main strategy moving forward. One of the largest PET producers in the world, I believe it's the second largest actually, Indorama Ventures, has signed multiple partnerships within the depolymerization space to meet the short-term demand for recycled content from the beverage industry. But it's really a long-term play is to bolt on Loop Industries process, one of the leading developers inside the space, to multiple global facilities it has located around the world. Now, Loop Industries also made a big announcement in September that, if successful, could substantially improve the total addressable market of depolymerization technologies. But I'm going to touch on this and postulate a little bit about the depolymerization space when we get into our end section, the scenario analysis, and for our future projection slides. So I'll be talking about that. And as you'll remember, depolymerization requires the cleavage of very specific bonds in the PET polymer chain. It's very specific. It really goes in and targets very specific bonds. And I like to think about this anecdotally as essentially you're going in with a scalpel and cutting PET polymer chains apart very delicately. The next advanced recycling technology, pyrolysis, conversely, I like to think about as going in with a hammer and breaking your polymer chains apart randomly. Pyrolysis does this by heating up really any carbon-based feedstocks in a reactor without the presence of oxygen, cleaving polymer chains randomly and basically producing a mixed hydrocarbon product, liquid product, which is called pyrolysis oil, which is going to range all the way from your C1, C2, low carbon, non-condensable gases, all the way up to C35 plus waxes. And pyrolysis, actually, I did some of this inside my academic career, began as a biomass technology, where treating sort of biomass waste feedstocks turning into a pyrolysis oil. And when you do this on biomass, the composition of the resulting pyrolysis oil, actually it has a lot of oxygen in it, and it makes sense for fuel applications. So when a lot of the developers first began, I'm talking early pyrolysis development, first began switching over to waste plastics as a feedstock, they were still targeting fuels, a lot of like number 2 heating oil and such. However, the pyrolysis oil produced from plastic waste can be split into its separate components via distillation, critically does not contain a lot of oxygen, and most developers are now splitting it into its different components and producing a wax, heavy naphtha, middle naphtha, light naphtha, and chemical streams, which can be sold to major oil and gas companies who will send this pyrolysis oil, depending on their preference, if they would like it to mix the heavy and middle naphtha component, for example, they'll send this pyrolysis oil through steam crackers in order to produce new products, whether it's plastics or chemicals. There are several variations with the pyrolysis. I am certainly generalizing here. You can adjust your process and target specific problem waste streams like polystyrene. You can add a catalyst to produce specific products. The catalyst is a little bit different. You're actually not lowering reaction temperature. There's a lot of catalyst fouling issues there, but actually you're adjusting the products formed with your catalyst and to produce something like a BTX stream rather than pyrolysis oil, so it might be a little bit easier to sell. And temperatures can range there's a pretty wide range from we basically group it into two different buckets. Slow pyrolysis, which operates in the 400 to 500 degrees Celsius range, operates for a little bit longer, so your energy costs are higher, but it has fairly high efficiencies. Or we have what's called fast pyrolysis, which is generally in the 700 to 750 C range, which, although your reaction times are much lower, you do a little bit more pre-treatment to reduce the volume so you can have quicker reaction times and spread heat more efficiently, but you're also going to end up producing a lot of char byproducts. So if you're operating in the temperature range, you generally have to do something with your char. And generally, we've seen this in the past that just throwing it into a fertilizer as a filler material doesn't work. You need to do something else, like use a Fischer-Tropsch process to turn into electricity or something like that. Now, pyrolysis is a high-temperature process which co-fires its non-condensable gases to help power the process. And this is critical because it means that uptime and large-scale operations are absolutely necessary for successful economics. Pyrolysis really does not work as a distributed technology. In general, you're going to be losing money if you're trying to operate on a 10,000, 15,000 ton per annum scale. This, alongside the fact that, as you can probably imagine, the oil and gas industry is urgently looking for ways to make their oil products more sustainable and utilize a lot of this pyrolysis oil, means that we've seen over the last 2 years, we've really seen a huge amount of capital being injected into this space by those large oil and gas companies. While most technology developers are small to medium-sized companies, we're really beginning to see the BPs, Cyclyx, Eastmans of the world really begin to take over, scale up in large-scale facilities. A lot of 200,000 ton per annum facilities, for example, are coming to Europe over the next several years. This model also assumes that as many of the small to mid-sized developers are currently experiencing and telling us that negative feedstock costs are going to be present, just like depolymerization. You see feedstock inside the revenue column. However, this is something that we do project to change with several massive pyrolysis facilities scheduled to come online over the next 5 years. We do expect eventually a positive market value to begin to be placed on this waste stream. It just is such a large volume that it would be difficult to retain it as a negative feedstock cost. A lot of the pyrolysis developers today, for example, are going to recyclers in a similar sort of model that we talked about to the carpeting waste producers. They'll say, hey, you have unrecyclable flexible films that you can't recycle, you need to throw in a landfill. We'll agree to take it for a smaller amount. Now, Plastic Energy is a great example of a small to mid-sized company with great feedstock flexibility and inter-process monitoring. And I want to emphasize that inter-process monitoring to ensure consistency inside of its pyrolysis oil product. It's really, as you can imagine, steam crackers are a very expensive asset. And a lot of these large oil and gas companies, they don't want to have any sort of contaminants like any sort of halogenated like PVC being processed that's going to disrupt it, degrade reactor walls, and really be a really expensive mistake. So inter-process monitoring has really become a staple among the leading developers inside this space. And Plastic Energy in particular has received a ton of funding over the past 2 years, has signed a partnership with Cyclyx to build a commercial pyrolysis plant in the Netherlands. Now, we've talked about both depolymerization and pyrolysis, which are fairly drastically different than mechanical recycling. There's clearly a different set of technologies. They're high temperature thermochemical processes. But I like to think about the third advanced recycling technology that we'll be talking about today, solvent-based recycling, as really just, you can think about it as mechanical recycling with a really advanced method of pretreatment. So this technology realistically is not as relevant as the other two advanced recycling technologies I've shown you thus far. It's probably not going to have as much of a commercial impact inside the next decade. So I won't spend as much time on solvent-based recycling, but I think it's really useful for hard to recycle materials. It might have some relevance to people on the line. So solvent-based recycling at its core really takes advantage of select solubility of certain plastics to recover the most valuable components of a hard to recycle plastic waste stream, like multi-layered plastic films. And so let's use a polyamide, low density polyethylene, bilayered film, something that you might find a lot inside of food packaging as an example. So first you would take this polyamide, low density polyethylene film, you'd grind it up, size reduce it, place it in a vessel, and then you're going to add a solvent which selectively dissolves polyethylene only at an elevated temperature. So you add the solvent, you heat it up, and then you're going to filter this solvent out, and the dissolved polyethylene stream is going to come out of the vessel. You simply lower the temperature, your polyethylene is going to precipitate out of the solution, and at that point, you're just a melting and re-extruding step away from a high-quality recycled plastic. Generally can be used inside of food-grade applications. And then again, now that you filter out the polyethylene, you have basically a vessel sitting full of polyamide. If there's enough polyamide to be worthwhile, you can add another solvent, obviously, that's going to selectively do the same sort of process and selectively purify that component of the waste. Now, as I'm describing this process, I'm sure that many people on the line are imagining you're going to run into a huge problem when there's an unwanted component of the waste, whether it's a plastic or some sort of organic contamination, that has a similar solubility to your target plastic. So the really key area of innovation here is developing very selective solvents for different types of plastics, especially if you want to go after post-consumer waste, and at the same time, scaling up the production of these very selective and specialized solvents so that it's not super expensive when you try to run your process. And as you might imagine, developers have been able to identify some extremely selective solvents that might be able to handle dirty or post-consumer waste streams. However, as I mentioned before and as I hinted at, these are extremely specialized solvents. They're extremely expensive, really low production volumes. And honestly, going after post-consumer waste at this time is unfeasible because of the cost of these solvents. Not only the cost of the solvents, especially right now with the early stage of these processes, a large amount of solvent is currently being lost to contamination in the distillation process. Therefore, to date, only post-industrial waste has really proven to be successfully processed at a significant scale, which is what our model here shows. Now, this isn't to say that there's no potential in solvent-based recycling methods, but the technology is just clearly at an earlier stage than the others that I presented on, and probably isn't going to have a real commercial impact in, let's say, the next decade. Still, I do want to call out one of the leading developers, APK, which is certainly doing its best to refute my opinion on the solvent-based recycling as they overcome some of the technical barriers by partnering with a de-inking company and signing an important partnership with MOL, although they still are operating at a relatively small pilot scale. So we've established what these advanced recycling technologies are. We've built cost models to explore their commercial viability. But as I mentioned, we really are in a weird recycling economic condition right now. A lot of these cost models necessarily aren't going to translate to what we'll be seeing over the next several years. So what we've done is I've adjusted some of the inputs based on where we expect prices and efficiencies to go to, in order to model and talk about how we see each of these technologies evolving over the next decade or so. And first, because I know there's a lot of information being thrown at you on this slide, this is like the graph you saw earlier. For each technology, we have the production costs and revenue numbers you've already seen on the left and the projected numbers on the right of each section. And I want to start with the box on the left, mechanical recycling, which has turned into a really booming market with substantial plans to increase capacity over the next several years. And the first point I want to keep reemphasizing is fairly obvious. As domestic mechanical recycling capacities increase to replace overseas recycling markets, we're going to see plastic scrap and recycled pellet prices return to some sort of equilibrium. For a variety of factors we don't have time to get into, I expect this price to sit somewhere above pre-China national sword levels, but much lower than they are today. Furthermore, advances to feed systems are going to allow new form factors such as monomaterial flexible films to be recycled. Think like plastic grocery bags or plastic carrier bags, though that's not really represented inside this graph. That's really a projection for low density polyethylene. Ultimately, new recycling technologies are coming to the market, but mechanical recycling is still going to dominate an easy to recycle plastic waste streams. Depolymerization technologies are going to continue to see refinement. A push towards one of these winning reactions that I mentioned is likely going to happen. And we're constantly still seeing new entries to the space each year. But ultimately, the depolymerization space seems to be limited by its dependence on niche, low-quality PET waste streams. Simply put, 100,000 tons of polyester carpeting waste in one localized area is just not realistic. So for depolymerization technologies to have a significant commercial impact, they really need to expand beyond these niche feedstocks while avoiding mainstream plastic waste streams like beverage containers. In essence, depolymerization needs to tap into the vastly under-recycled polyester textile waste market. However, as I mentioned, as I try to emphasize, any type of nylon contamination in your feedstock is going to ruin your depolymerization product stream. And so we've seen two strategies towards this, and this is getting towards the exciting announcement, is that some developers like IBM, for example, are designing their process to be softer or a little bit slower, and it doesn't include as many harsh chemicals that are going to break down nylon. And so it does have a small contamination allowance. However, Loop Industries, with their announcement, is taking a different approach. It recently, in September, signed a partnership with Suez, a major, you've probably heard of them, a major European waste management company with an extensive expertise in automated sorting systems using near-infrared cameras. And in the past, near-infrared could not actually see black items, as the black colorant absorbs light waves and provides no signature. So obviously when you're treating clothing, dark clothing items, it would not be able to identify what's contained within that dark clothing item. However, over the past year and a half, it has begun installing equipment that can overcome this technology barrier. And this would be huge for textile recycling and expanding depolymerization addressable market size. Manual sorting cannot properly identify blended fabrics, with tags often being lost during disposal, but near infrared could do the job. Now that the main limitation has been overcome, depolymerization could theoretically enter the textile recycling space. And I do want to say that this is a very recent development with a lot of speculation on my end. In fact, Loop Industries has not even indicated they're going after, although there's been some hints, they haven't definitively said that they're going to be going after textile waste streams with this partnership and the commercial facility that's planned for 2023. But all signs point to, and the real potential in this space for large-scale operations points to the textile market. As I mentioned, commercial facility using this technology, going after this feedstock, won't be operational until 2023 at its earliest. Everything goes according to plan, which is certainly might not be the case. And in the meantime, we do expect developers to continue scaling up through this small scale distributed rather than the large scale expansions. But there's substantially more long-term potential if depolymerization can begin to tap into textile waste streams. Now, pyrolysis is clearly going to have a large role to play with investments from major oil and gas companies. However, low oil prices and some plastic scrap trade restrictions from the Basel Convention have hurt prospects in recent months. Regardless, the momentum of pyrolysis, bringing it to a commercial scale is basically, we know that it's going to be brought to a commercial scale. It's really only a question of outside economic factors that are going to determine its overall economic viability and how much of that market it can capture. And finally, solvent-based recycling has some applications today that dealing with clean but mixed streams like multi-layered industrial packaging waste. However, it's honestly, it's unlikely to play a role for the foreseeable future. So, what does this mean for you? It really depends on where organization sits in the value chain. I'm told we have a diverse set of stakeholders viewing this conference. So let me summarize with a couple of key points. First off, this was a presentation on the future of plastic recycling, not necessarily all sustainable feedstocks. We probably need twice the amount of time to cover compostable, biodegradable, and renewable content options, but to generalize, and hopefully not to get myself in trouble, these options all struggle mightily to compete on price with their petroleum-based counterparts. Yes, some applications and geographies, biodegradable options certainly make sense. Thermoformed molded pulp products are going to get cheaper as paper markets continues to decline, and it will replace some plastic packaging. And certain compostable plastics are being incentivized in certain geographies like China. But overall, traditional plastic materials are here to stay, although an ever-increasing percentage of them is going to be coming from recycled sources. And speaking of those recycled sources, mechanical recycling is going to continue to dominate the easy-to-recycle plastic waste streams. The advanced recycling technologies we talked about today will likely capture some low-value recycling streams that usually go into mechanical recycling, like commingled 3 through 7s, but they are primarily expanding the scope of recycling rather than replacing traditional methods. Legislation, as should go without saying, is going to have a huge impact on the impact and success and spread of these technologies. It may be the hardest factor to track, especially in the US when you're dealing with local, state, and federal policies, which all mix and combine and have an influence. But they're very essential to fully understanding industry pressure that's going into the development. And finally, I want to emphasize how many moving parts there are inside the recycling industry. Scrap and recycled pellet prices are changing rapidly. Multiple expansions are being planned each year, and brands are changing their traditional material demand. While this can certainly be intimidating and will undoubtedly see a couple of major material suppliers stumble, there's also a huge opportunity to capture new customers, more market share, if you're able to stay ahead of the game. So I'll leave everybody with that. Hopefully we'll be able to follow up in the Q&A section, and I'll turn it back over to Donna. Thank you.
Thank you, Charlie. And now I think Ashley's going to give control to Joe.
And I am doing that now. So Joe, you should be able to take it away.
Great, excellent. Well, good morning, everybody. Pleasure to be here. Charlie just walked through a tremendous amount of information, and I'm going to dovetail in it with maybe a slight different perspective. As Donna introed me, I have a long tenure in waste to value technologies, most notably with waste management. We invested in upwards of 65 plus companies. And within that portfolio, we had about 35% of those technology companies developing thermochemical approaches, as Charlie walked through. And, we invested in pyrolysis, gasification, plasma, multiple companies. And I think there's a lot of fallacy around understanding what those technologies fundamentally are, how they're different. And more notably, I think once you get past comfort with technical efficacy and can do it in a way that is economically appropriate for your strategy, the biggest risk, the biggest challenge ends up being feedstock. And so what I'll do today is try to transition from a technology focused discussion really a little bit more to the feedstock side. I was introduced as the president of Cyclyx International. It's a new company, not well known. I'm actually transitioning into that company as an affiliate of Agilix Corporation. Agilix has been around for 15 years and has commercialized various product pathways in converting mixed plastics to various hydrocarbon products, which we'll get into. We started very appropriately where Charlie highlighted. We were looking at pursuing non-recyclable plastics and creating a crude oil at the time. And it took us quite a while to do it. We did commercialize that platform, but as we started to get smart and a lot more experience with managing feedstocks, we started to see that there was a much better opportunity going after plastic to plastic approaches. And so today, the company has a core technology. It has a core technology, but when we talk about our business, we talk about it in a multiple product platform, in that we've combined a very sophisticated feedstock management system that allows us flexibility using a thermochemical technology package to produce multiple products. And so we'll start there. I'm actually going to start where Charlie left off and talking about mechanical recycling. For sure, that's true. The markets that are mature are mature. But if you sort of take a step back and you look at the recyclability of plastics today internationally, you're only really averaging about 10% with that mechanical recycling approach. And for sure, if you had design for recyclability and you had better, more advanced MRFs and perfs, sure, that number could increase. But it's fundamentally not going to get to what I think Agilyx's goal is. We have a mission to sort of defer upwards of 95% of the plastics from a landfill and actually bring it to a higher value product. And so mechanical recycling is great, but it sort of relies on the fact that you're creating a high quality, homogeneic raw material to be introduced to make what I would sort of consider to be downgraded products. You're taking a PET bottle and making a carpet. Wouldn't it be better if we could find a chemical recycling technology pathway that could take the carpet back to the bottle? And so when we think about chemical recycling as a broad category, and we look at all the different product pathways that could be pursued, we believe that the recyclability of plastics, even in today's markets, could increase from 10 to 90%. We can get into sort of the raw economics, and that obviously has to do with geography, scale, all sorts of factors. But I would say generally, thermochemical technologies are on they're in a 15-year innovation cycle. And so you're starting to see upwards of 70 companies come to the market with some form of technical package. Even though that's true, and even if you assume that this could be true, what's the problem? Why isn't pyrolysis in this case for plastics not more mature than it is? And you very quickly get into the problem of the feedstocks, the complexity of the feedstocks themselves. So when people think of plastic waste, it's natural for them to think about what they throw away at their house, and they just assume that all plastic waste is sort of homogeneic. You can go to a MRF and it's all the same. And one of the things that we learned the hard way at Agilyx was, indeed, plastic wastes, the slipstreams of wastes are dramatically variable, both in forms of the types of polymers, stabilizers, and things that are designed into these packages. But think about it, you're throwing away millions of different products. You're throwing away a number 7 bottle that has inks and dyes on the label, and then you've got some residual material in the bottle, and that's mixed with 900,000 other pieces of plastic. And you can go to the MRF and you can try to separate them out, and then you have to clean, wash, pelletize, and then ship. All of a sudden now you're touching these plastic materials many times and adding a lot of cost, and ergo it makes it really difficult for somebody to chemically recycle them. Add to that complexity then, once you start to convert these materials, it's not that easy, right? There's lots of different product pathways, and it's easy to generalize to say, yeah, let's make a some sort of hydrocarbon stew that you have a light, medium, and heavy distillate cuts that you can separate and put it into an integrated refinery. But if what we're really trying to do is look at plastics as a renewable resource back to virgin-like plastics, then you really have to think about how the system manages the aggregation and pre-processing of that material and the product pathways that they can go to. And so Agilyx over the last 15 years is really, that's what it's done. And so today we do actually have a technology platform. It's a pretty robust platform. It's flexible, but its priority and its orientation is to recycle polymers back to virgin-like polymers. We're one of the few technologies. There are many emerging. As I said, there's about 70 companies out there. And the fallacy is that pyrolysis is all the same, or that all thermochemical processes are the same. It's really not true. And we've done a fairly extensive scan in these technologies. And what you'd find is 30 discrete different designs of pyrolysis. And those design variations would, impact things like, is it batch or continuous? Is it under pressure or not? Is it under vacuum or not? There are all these factors and operating conditions, the temperature regime themselves, all impact the type of efficiency and product quality that you get. And so understanding this from my waste management days, one of the embarrassing things was that we felt like one of the strategic levers we could pull for our downstream technology partners was to feed them the appropriate feedstock. Well, guess what? We can go to a MRF and we can separate materials into basically homogeneous feedstocks, and yet the chemical characterization is very different. And so Agilyx has spent the last 15 years developing the largest thermochemical conversion of slipstreams of plastics to known hydrocarbon derivatives. And it has then used that system and incorporated it into our technology package to be able to produce products in all three of the main categories of hydrocarbons, right? We can go back to virgin-like plastics. We can make plastic intermediates like naphtha that obviously is indirectly back to plastics. And then, of course, you will always have some slipstream of waste plastics that really aren't appropriate for high quality products, but it can be used for fuels. And we do all three. But I'm not really here to talk and have a commercial on Agilyx's technology. I'm going to talk a little bit about where we sit and what some of the fragmented aspects of the industry are. So where do we sit? We're not some small independent technology company that's going to design, build, own, operate, take plastics from the market and create some sort of merchant product that we try to sell. Indeed, that's not the case. We sit within two industries that has always been a chicken or the egg. You've got waste and recycling companies who actually physically have possession of the material that could be used, i.e. plastics. But they're not petrochem companies. They're not going to build a chemical plant. They don't want to run them. And for the most part, they don't chemically understand what's in the various plastics that they have. Their knowledge really is around separating mechanically into the known mature markets, which we've already talked about is only 10%. And then you have the chemical majors, right? So these companies are really great at industrial production. However, they have no understanding or interest, frankly, in sourcing feed from the waste industry. They don't understand the chemical characterization either, nor are they a waste company that wants to get into some pretty complex supply chain to source it. So Agilyx has put these two competencies together on the feedstock management side, which is what Cyclyx is. It's actually an actual company that sources for ourselves. And we then design the product pathways for our customers. And so we dedicate our know-how both on feedstock and technology, combine them and custom develop for our downstream petrochem partners. And we can produce anything from we can take, polystyrene back to virgin-like polystyrene, or we could do a lesser quality raw material that gets fed in and be further refined. So we've got great flexibility, but that flexibility has everything to do with understanding feedstocks. And so your technology could work tremendously well to make an industrial wax or a fuel or maybe a PET co-monomer. But if you don't understand and can control the variability of the feed coming in at the chemical level, not at the, it's really, if you think about the complexity of the contaminants of concern, that you can't just put it into the soup and mitigate it out, then it all starts to become, how do you aggregate a proper amount of feedstock, pre-process it for the quality and at a cost that allows the system to work. And I would argue that it's too simple to just conclude you can go to the market and get paid $50 a ton to take mixed feed. It took us 10 years to figure this out before we could make a stable product. And I think if there's a challenge for the competitors in this space, it won't be the technical efficacy of their black box. It will be how can they manage their plastics. And so for us, the way we think about it, not being too prescriptive or sensitive, the feedstocks themselves all have primary parameters that we track. We then have to bounce that up against the operating conditions under which those polymers would be mixed and converted with a whole bunch of other characteristics. And so when you start looking at 12, 20, 50 parameters, the perturbations of possible chemical reactions that you actually have to manage is quite high. I would tell you though, if you could figure that out, it unlocks the key for chemical recycling to go from 10 to 90%. And that's what I think with all due respect to everybody here, the industry is missing. It's not about enhancing the throughput of mechanical recycling. All you're going to do is make more carpet. Not that that's a bad thing. But if you want to get back to virgin-like polymers, you really need to understand how to control the chemistry of what you have. And so for us, what we've been able to do, and you'll see lots of announcements here. We have a lot of existing petrochem partners, and we have some emerging that will be announced over the next couple of months. We've created this, we've imported this feedstock expertise in predictive modeling capabilities. And a little bit ago, we announced a joint partnership with GE, who's actually taking their existing artificial intelligence platform and embedding it into our database. And so today we can predict either way. If you came to us and said you wanted a hydrocarbon product of a certain specificity with a certain profile, we can reverse engineer the feed that needs to go in it and vice versa. We get approached all the time from companies who want to understand or from municipalities, what can their products be used for? We can take it in, we can chemically characterize it, and we can predictively model it. And it really allows us to be very, very efficient without adding all of those extra steps into what mechanical recycling does today. And so what you'll see, Cyclyx then is a new business. It will be a consortium business. It will basically be a company that works with 100 other companies to create supply chains and product realities, with the highest priority being plastic back to virgin plastic. And it then will be a system, right? So it will have the knowledge of the AI tool set as a start. And then it will then apply that same AI tool set to look at the supply chain a little bit differently. One of the advantages that a lot of the non-catalytic based pyrolysis technologies have is you don't quite need the level of cleanliness, so you don't need to wash and pelletize to the degree that mechanical recycling does. So with that mindset, then you can start to be creative with the supply chain and not try to build additional MRFs and PERFs, but source directly, which is indeed what we do. So with that, I guess I just conclude to say I don't disagree with some of the overtures and the profiling that Charlie has, because that is reality. And I think you'll see these companies in thermochemical mature pretty quickly, given the financial muscle that is being applied into the marketplace today. But I do think that the way we think about waste plastics and how to aggregate them and what they can be used for and what path they should take really needs to be looked at completely differently. And I think if we were to be able to do that as a consortium effort, you really could dramatically impact the recyclability of plastics. And so we've actually, you'll see this brand identity come up. We're going to try to help bring plastics from 10 to 90% recycled. So with that, I'll conclude because I know that we are interested in having a Q&A session here. And so Donna, I'd hand it back to you.
Thank you, Joe. And thanks, Charles. This has, I think, been quite insightful. I can assure you it's brought us to a lot of questions. So I think that will help clarify what you've told us in many ways. There are some fundamental things, and then there are some more specialty things. But I'll just sort of plow through them. On the mechanical recycling slide, why, and this is for Charles, really, what's the definition of residue? How is it measured and quantified? And such that we understand why mechanical recycling is not sufficient.
Helpful if I take myself off mute. Yeah. So I was looking at that question before, and I was trying to find the mechanical recycling slide. I don't believe that I mentioned residue on that slide, so I'm not exactly sure what it's asking. But overall, on the overall capacity of mechanical recycling not being efficient, it's a combination of overall right now, just the capacity of mechanical recycling is much lower than has been said in the past. And I love Joe's viewpoint as he's presenting his slides, because you can see that we have a little bit of a different viewpoint, but something that he really emphasized was mechanical recycling. A lot of times the recycled pellets that you're producing, they don't have the type of qualities that can be used for all the applications, all of this recycled applications that we want to use today. That's really why that's really one of the big stopgaps of why the thermochemical recycling methods are becoming a lot more popular and really are essential to reach some of those higher grade applications.
Good, thanks. There were some questions around definitions of MRF and MERV, and probably that's good to help people get the basis.
Yeah, so MRF is just MRF, Material Recovery Facility. And so as again, that's the first part of the value chain. So they're the guys that'll go around and collect blue bins, for example, throw inside the recycling trucks, bring it back to their facility, sort everything out, do a little bit of washing, and then bale up all of that plastic waste and sell it off to the recyclers. There's a lot of times MRFs will also be recyclers. Vertical integration obviously is going to make sense there, but in general, we like to think about it as two separate parts of the industry.
And this question might go to either one of you, but there's a question about pyrolysis and whether it's truly circular if the product is fuel. And I think you both addressed that a bit. Who wants to take it?
Yeah, I don't mind leading that. I think another fallacy sort of amongst these technical options is that all plastics are sort of created equal and can be used for product pathways, and it's clearly not true. And so there, depending on how material is sourced and separated and pre-processed, plastic to plastic, obviously you need to have the specific polymer that you're chasing as your main ingredient. As you start to get into the intermediates and the fuel, you can obviously take a larger swath of mixed plastics. Naphtha is a lighter cut, it's a higher quality cut, and depending on what you're using for technology in a remediation pathway, it's a certain quality. Fuels generally can take a lesser quality. So I guess the way I would think about it is, if you wanted to look and divert 100% of the plastics from landfill, then fuel would be a necessary portion of the mix. It's just hard if you're going to build a large scale facility, as Charles points out, that you're designing the facility without understanding the feedstock. And so for us, the fuel is 50 to 70% lower carbon, so it's a better fuel. But that is truly not circular, but the intermediates and the plastic to plastic is.
Yeah.
Thank you. Yep. There's another question. There is a question. We did a lot, or you guys talked a lot about technologies and economics, which is obviously a main driver. What about life cycle assessment, and how might that push the balance one way or another?
Yeah, When I look at a lot of these advanced recycling technologies, a lot of times what these technologies are doing fundamentally is they're diverting plastics away from a landfill. And a lot of times when people look at, the LCA for a high temperature pyrolysis operation, you might see, oh, this has a large carbon footprint, et cetera. First thing is a lot of non-condensable gases are going to be recycled back into the system. So they are efficient. They are trying to reduce that. But more importantly, when you look at these plastics and you sort of look at their footprint when they end up inside of a landfill, and not only, carbon dioxide that gets released, but also the methane, ethylene that gets released into the environment when they're sitting inside of a landfill is pretty substantial. So I would caution against just looking at it from a straight LCA standpoint of this process. A lot of times you have to do the comparison of what happens if it doesn't go through this life cycle analysis? What happens if it ends up inside the landfill? It's going to have a much worse overall picture.
So does that play into technology selections around what might be able to accommodate more stuff that would otherwise have to go to the landfill? Does that sort of trump the life cycle of the economics assessment in terms of you're pulling something out that otherwise has to be landfilled?
Yes, at some point. I would say that I would never want to overrule the economic analysis, because at the end of the day, life cycle analysis and, there are no real regulations around plastic production today, around carbon footprint of plastic production. So until we get some sort of push from a legislative perspective, whether it's Europe, United States, wherever you're operating, the economics are going to need to make sense first.
Yeah, and let me talk to that a bit, because we are challenged with this, and most of my career has been trying to commercialize these early stage technologies, which just by their nature are inefficient, not unlike wind and solar here a few years ago. But I think the way recycled content is being viewed really deserves a relook at what economic reality is, right? I mean, there are our plant, for example, just recently got ISCC Plus certified. So with our partner, Americas Styrenics, we can take not just clean foam and turn it back to clean foam, but we can actually take a used flower pot that is clearly not recyclable with dirt and fertilizer residue, and we can actually convert it back to virgin food grade monomers. So we can actually upcycle these. That is now ISCC Plus certified. On par, it competes with commodity pricing, but that by itself isn't the value, right? I mean, Europe has these strict mandates on recycled content that most companies are not going to be able to meet. So there's liability, risk, exposure avoidance. There's all sorts of other strategic, market share and things that sort of come along with the recycled content itself. So I think if we were looking at the economics purely from a commodity-based lens, it's misleading. I think you have to look more broadly at what it's accomplishing in the market itself. And as far as the LCA, for sure, we need much more sophisticated models, but there has been quite a few done on many different technologies. And the one good thing about plastics, it's already a refined material. So it just happens to have a lower LCA quite considerably than virgin manufacturing.
Joe, you mentioned ISCC and ISCC Plus. Do customers of Agilex also have to be ISCC certified to take advantage of that accreditation system?
So we do. So the way Agilex operates today is we've sort of separated our business. And so the facility that I referenced before, in coordination with Americas Styrenics, we've actually directly sourced material from 500 suppliers. And each one of those suppliers needs to be certified by that certification to be qualified material into the facility.
And going downstream from you as well. Yeah, okay.
For sure, yeah. All the way through there's a mass balance, there's a sort of a molecular accounting balance. So we deliver so many pounds to AmSty, they process it, then they have that certified that they can sell on the market.
Thanks.
And actually, Donna, if you don't mind, I'd actually like to ask Joe a quick question here, because something that I have a little bit of outside perspective on, and something that we always talk about constantly, is that legislation is going to play a large role in the implementation of these advanced recycling technologies. Right now, and to the best of my knowledge, if you take plastic, you go through pyrolysis, you produce pyrolysis oil, send it through a steam cracker, produce new plastics, that's not considered by law is not considered recycled content. Do you have any sort of idea or any sort of, your finger to the wind of, is that changing? Where do you expect that to go inside of Europe, inside of the United States?
I do think it's changing. I know, I can't preach sensitivities, but I know that there are some bigger companies that we're working with who are getting those qualifications. They will include both sort of the molecular accounting, just because the scale imbalance is so large. I mean, with America's Styrenics, a 50-ton per day input feed is only about 0.5% of their raw material daily need. So you have to balance it. But I also feel like we're seeing that they're separable. Once you have the credits, you can sell them all over the world. And so I think that is very similar to what we saw years ago under the RFS2 program, where Waste Management was producing biogas, converting it to electricity. And it's a very similar program. So I do actually think that you'll see a huge scale to that activity in the very near term.
Great. I really think that's essential for the space to move forward.
I would agree.
And Charlie, a question for you, I think, around what happens to once you have feedstock that coming from pyrolysis or whatever, and it goes to a steam cracker, presumably to generate feedstocks that go to polymerization. Is there a lot of upgrade required for the steam cracker, and to what extent might that also impact economics?
So this is actually a really interesting question. It's something we've been looking at a lot. Unfortunately, a lot of times when you talk to, you have to remember that at Lux Research, my viewpoint is I'm talking to all these pyrolysis developers, and I'm talking to them. And a lot of times the agreements with these large oil and gas companies are undisclosed under NDA. So we basically get hints about this. But first things clear is that every oil and gas company, whatever steam cracker, they're going to have different preferences for the feedstock that they like to accept. For example, that partnership with Plastic Energy and Shell. For example, I know that Shell, they generally like a heavier naphtha oil to send through their steam crackers. They like a middle mixed with heavy, and actually some of the wax product mixed into that stream to send through their steam cracker. So there's a lot of different personalization on adjusting that pyrolysis oil. And that's something that I talked about with the inter-process monitoring is really essential for pyrolysis, to be able to adjust and fit your customer's need with your pyrolysis oil and make sure you don't make any mistakes and have components that can't go into that specific steam cracker. But Joe, do you have any insight into that? Because I know you're a little bit farther downstream from me. I know you've had some of those conversations. I don't want to pressure you into including anything that you have under NDA, but do you have any? Yeah, no, it's actually a great area of discussion. It's actually how we have matured our thinking on our business model. So years ago, we did design, build, own, operate facilities. And our assumption was we could make this pyrolysis oil and sell it on the open market. And what we realized very, very quickly is that even if you went to a steam cracker, our naphtha now has been qualified by quite a few companies, but the specification of the naphtha feed that they need is actually marketably different, where they're not fungible. I couldn't actually sell from one customer to another. So we got away from that. And so we designed very specifically the output for our partners. And what we tend to find is that we can dial in on the product specification that they need as input. And then as you work upstream to the feedstock, inevitably that means you have to have a slightly different mixture of feed that would go into one naphtha feed than another. So this whole idea about controlling the feedstock becomes very important when you start to hit product specifications because of how tight some of these specifications are. Yeah, exactly. And that was even when we were building the cost, sort of our home-baked cost model at Lux Research about the pyrolysis model. That was one thing that when we began to write this cost model, we saw this trend of splitting your stream up, selling your pyrolysis oil to oil and gas developers. It was almost impossible. And eventually we discarded the idea of actually trying to split up this stream. What we did is we split all the streams, combined it back into, and I probably should have mentioned this, but we combined it back into a number 2 heating oil because we can sell it on the open market because we can get an open market price for it. So us, market analysts, this is all we do for our job. We couldn't find a market value in how to split up the different streams. So
exactly,
there's a lot of customization that's going on.
Yeah, for sure.
It's so interesting that I think probably both of you, you're talking now about optimizing blends to feed feedstocks, to make feedstocks, and you're talking about these variety of technologies that are better for particular kinds of waste. Do you have a vision? What does the future look like? Do you have a recycling, even if it's an advanced recycling site that has multiple technologies that they practice at the same site to accommodate different outputs and different inputs? Or does it in fact all end up in some big gargantuan pyrolysis unit or something?
So it really depends on what you're trying to optimize there. You really could go either way. The main issue with plastics is that they're so light that to do anything sort of appreciably large volume would require a pretty significant supply chain to feed it. So you could either do that and focus your time and make the supply chain efficient to feed a very large regional or national production, or you could go the other way and have small co-located technologies closer into the waste sheds. And I think we're somewhere in the middle. I think there's an application for all of those things, particularly if you're going to go polymer to polymer. However, that said, I think if you think about the economics, the other thing I want to, it's nuanced, but it's an important, when we think about economics, most people tend to think that those are standalone for-profit companies. I don't know that I would view it that way. We're making a product that we're trying to optimize and internalize for our downstream partners. And so they don't view it the same way we view it. So you have to have a different lens to the product, how it gets internalized, talk about scale, and then look at the waste shed. And so a lot of what we do with our partners, we spend as much time on waste shed analysis for them as we do on the product specification, because it's, I would say from an economic impact perspective, it's at least 50% of the risk, if not more.
Mm-hmm. And this is one of the scenarios that I know from my conclusion and from Joe's conclusions of his talk. He said that, I believe you mentioned that 90% of the market could be captured by various chemical recycling technologies, where I say this at my conclusion that mechanical recycling is going to remain dominant. And so this is, I love to have this different perspective for the presentation. It shows how much, discussion there is inside the industry about in all the different options that there are. In general, when you have, like imagine just like a large waste accumulation center, let's say the Port of Rotterdam inside of Europe is, probably everybody's going to know that, located on waterways, located on rail systems where you can get a large accumulation. We're talking 500, 600,000 tons of mixed plastic waste, feedstocks. What we've seen, or what I've seen, and sort of what we've imagined going forward, is that part of those, those cleaner waste feedstocks might be treated by mechanical recycling, because although you're not going to be able to go to your, virgin quality plastics, sometimes all right is okay. So you do need to produce carpeting, you do need to produce plastic lumber. There are applications, and if you have a really clean PET feedstock, you can even go, food grade rPET with mechanical recycling. It's a little bit more expensive. It's a little bit, there's some intricacies there, but that is possible. So it's really an open bag. There is something to be said about just throwing everything in a pyrolysis reactor and kind of forgetting about it. But I think at least from my perspective going forward, it is going to be sort of a mixed bag, different technologies really operating inside the niche that they operate really well in.
Yeah, Charles, if I gave the impression, I didn't mean to, and I'm remiss, but when we talk about 90% recyclability, it absolutely includes existing and even increasing mechanical options. That wasn't to say that chemical recycling would replace mechanical. We were just simply saying that mechanical recycling by itself, even if, today, again, it's 10% effective worldwide, with 400 million tons being generated every year, you could triple that, and you still have 70% of the market that's not even being addressed. And so I think it is a combination of chemical recycling and mechanical recycling that would be required to work together to get to that 90–95% for sure.
There are a couple of questions that might be interesting also in terms of particularly difficult materials like rubbers, like chlorine-containing materials. Is that going to have to be solved through design for recyclability kinds of approaches, or do you think, or can sortation someday deal with it, or is it going to be through the recycling techniques? How do we deal with those hard to recycle materials?
Yeah, I'll go ahead and take a stab at this one. I'll say that most materials, when you look at it, let's PVC, for example, if you're able to obtain a large volume of PVC, just that single stream into one facility, you can process it with a variety of methods. Most materials out there have some sort of recycling technology that can address them. The issue is volume. It's overall volume, separating it out, getting that one particular plastic that you care about separate from the rest of the stream. So when you look at some of these problem waste streams, though, that like PVC, polystyrenes even, a couple of these problem waste streams, I don't really expect that the large volumes are going to be available to really make that type of specialized recycling process worthwhile. And Joe, I'd love to hear your thoughts on this, but personally, and I'll throw out a little bit of a bold opinion, is I could imagine a lot of these plastics eventually being phased out and redesigned for recyclability, redesigned for end of life. You know, if you're including PVC in your product, it's going to be an issue. It's going to be very difficult to recycle. It's going to mess up waste streams. So
no, it is true, and I think there will be a combination. I think the challenge, the short-term challenge with design for recyclability is that unless you're capturing it in a homogeneic way, the second you throw it and mix it with a bunch of things that were not designed for recycling, it becomes non-recyclable again, or challenging. And so what we tend to see is there's a couple different things going on. Design for recyclability for sure. You're seeing, but take, for example, fire retardants, right? I don't envision, unless we design a different type of fire retardant, that'll continue to be in plastics, and that we can process it in our system. The problem is our pyro oil now has fire retardants. So I either have to try to remediate it out, which you're seeing downstream remediation development efforts happen, or you find product pathways that could allow that fire retardant to be in it because it's part of the spec. So I think it's matching the needs and the scale to the product pathway. I think that's at least part of the challenge today. When we're talking about pyrolysis, we're overgeneralizing, and I think you have to be very specific about where you are and what you're producing.
Guys, this has been great conversation, and I'm cognizant of the time and the fact that we're running to the end of the time frame, and a lot of people are going to probably have to leave. So let's leave with one question. There have been environmental concerns expressed by NGOs or by whomever about advanced recycling almost conceptually. Could each of you share your vision for where we are 20 years from now? How do these advanced recycling techniques really play out over the next 20 years, and what does the recycling space look like? Charles, you want to go first?
Yeah, sure. I'll take a first stab at it. And although there is a lot of talk about, and we've sort of addressed the question before about overall LCA of these processes, ultimately, I believe that we're going to have sort of a material transition where right now we are 99% of plastic originating from petroleum-based sources dominating inside the world. Eventually, although I did mention some other sustainable feedstocks and sustainable product options coming into play, plastics are just such well designed, and they do such a good job for what they need to do for the applications that it's going to be very difficult to replace them with other materials. So when you're looking at the LCA of these advanced recycling options, again, you can't look at it in a vacuum. You can't just say, you know, this is the LCA of this material production. You have to compare it to LCAs of oil extraction, LCAs of, you know, traditional crude oil, things like that, in order to get an overall picture. As we go forward, I do expect, like Joe mentioned, whether this is a 15, 20, 30-year timeline, I do expect us to eventually transition away from petroleum as our main feedstock to plastics as the raw material and feedstock.
Yeah, I have a similar view. I think what you'll see is that these bigger downstream petrochem companies will integrate into their existing refineries either discrete add-on technologies or enabling technologies to their existing assets where plastic is a main feed for that source, that the supply chains will start to mature up and around that offtake, and that the market will be much more efficient, and it will be and I think that's within 15 years for sure at scale.
Great. So this has been a fascinating discussion. I thank you both. I think I've heard, or I'm interpreting what you say, that this is sort of the technology that will enable circularity in what I guess a lot of people think is this purest state, where we actually just keep the plastics going around. So very interesting, and we'll be looking forward to the next 15 years and see how it plays out. Thank you both.
Excellent. Thanks for having us.
Sounds good. Thanks, Donna. Thanks, Joe.
Thank you all.
Thanks,
I just wanted to hop on here at the end just to kind of close this out and thank everyone again, including Donna, Charlie, Joe. I know if anybody needs me for the next, 6 days, I'll just be sitting here in my office replaying this on loop until I learn everything that you said. So thank you guys again. And for those of you who are tracking the Refocus webinar series, our final episode is scheduled for November. Date is to be determined, but we are working with the education or the executive committee to come up with what I think is going to be a really good session around policy. So stay tuned for more, and thanks again for joining us today. You guys have a good rest of the week.
Thanks.
Thanks
Bye,
all.
everybody.
Thanks. Bye-bye.